In this video, we're going to be introducing a concept called work, which is something a little bit different. And specifically, we're going to be explaining it right now only using Newtonian physics and force concepts. And then there will be a separate video later about how to think about it from the standpoint of energy and conservation of energy. So when you're thinking about it from the force standpoint, the first thing I need to remind you of is remember that you can think of acceleration as having two components. One is perpendicular to the motion, perpendicular to the velocity, and this one is referred to as the centripetal acceleration, and it causes turning, but no change in speed. And then second of all, you have one that is parallel or anti-parallel to the velocity, which sometimes we refer to as tangential acceleration in the case of circular motion anyway. And this one causes a speed change, but no turning. Okay, now, what I want to add to that story now is, well, this may not be in addition to the story, but since F equals ma, you can also think of forces as having the same properties. They have the same property where you can view any force vector as really having two components, one that's causing the object to speed up and slow down, or at least trying to cause the object to speed up and slow down, and one component that's trying to cause the object to turn, depending on whether the force is in the same direction as the motion or whether the force is perpendicular to the motion. Okay, now we already know how to handle the cases where you have turning, because then you sort of get circular motion and you can bring in all that stuff about centripetal acceleration and circular motion. I want to talk more here about specifically this component of forces, the component that in the world of circular motion we call the tangential component of the force, but importantly for our discussion right now, it's the component that causes an object to change its speed. Okay, when a force has a component which is changing, or maybe I should throw in here trying to change, because the total net force on the object could be zero, in which case its speed is not actually changing, but there might still be forces on it that are trying to change its speed, but they're offsetting each other. So when a force has a component which is changing or trying to change the speed of the object, we say that work is done on the object by the force. Okay, we say that work is done. So the first thing I wanted to basically define work as here then is when you hear that work is done on an object, if you're thinking about forces, the first thing that should pop into your mind is that there is some force which is either pushing the object forward and trying to speed it up, or pulling the object backwards and trying to slow it down. That's like the key concept for what work is from the standpoint of forces. If you have a force that's only centripetal, only perpendicular to the object's motion, that force is not going to do any work on the object. Okay. If the work is positive, I should be a little bit careful with the phrasing here. If the work done on the object is positive, that corresponds to speed up, or an attempt to speed it up, so that the force is pushing the object forward in the same direction as the velocity. Let me add that. Force is pushing forward in the same direction as velocity. And if the work done on the object is negative, that corresponds to a slowdown. So that would be when the force is pushing backward in the opposite direction as the velocity. Okay, so those are the two possibilities. And then, of course, you can have no force component in the same direction as the velocity, in which case you have zero work being done. So that's what work is conceptually. The next question is, okay, well, how do you actually calculate it quantitatively? How do you actually calculate it quantitatively? And there's some suggestion here of how you would start to go about doing that. You can see that breaking the force into components, one component parallel to the velocity vector and one component perpendicular to the velocity vector, that's going to be a part of the story. But there's actually a smarter way to do this. Okay, if and only if the force vector is constant, this is the only case I'm going to cover in this video and in this course, because if the force vector is not a constant vector, the math gets more complicated and you have to bring some calculus in. So if and only if the force vector is constant, the work done on the object by the force can be calculated as, and it's going to be calculated using the dot product, which was just covered in previous videos. The work done, W, is going to be equal to the force vector, whose work we are interested in, dotted into the object's displacement vector. Okay, the displacement vector. Now remember, the displacement vector points directly from the initial position to the final position in the process. So when you're talking in this case here about just considering a constant force acting over a whole process, you don't have to worry about the actual path that the object traveled. You only have to worry about where did it start, where did it end, what's the displacement vector between those two things, and then multiply that by the force vector, and you're done. If you want a more detailed formula, this is really the best way to think about it, I think, but it might be a little bit too mathematical for some people. So other ways that you sometimes see it written, a lot of people will write it as something like maybe F. It's a little bit messy, a little bit neater. Somehow my pen thickness changed. F parallel times D, where here, if you go back to the dot product video, I talked about this terminology, that really what the dot product is doing is it's picking out the component of vector A that's parallel to vector B and then multiplying them together. Notice that that's exactly what we want to do based on the conceptual description above. That's why we're using the dot product. So the dot product does this automatically, but you can also do it manually if you want to. You can break the force vector into components yourself, and then you can multiply. D here actually means the magnitude of the displacement vector, which is a little bit of a weird way to say it. But this, I want to say it this way because this is how most people kind of say it. So D is the magnitude of the displacement vector. And you can also write this, I don't really care for this formulation of the formula, but this is how so many people memorize this formula. I wanted to mention it. A lot of people will say it as FD cosine theta or something like that. The theta there represents the angle between the force vector and the displacement vector, because that's going back to the dot product formula from the previous videos, that the dot product can be calculated as AB cosine theta. That's why that cosine theta is there. Just be extremely careful that you know what that theta means if you're going to use that version of the formula. I've seen many, many, many students who will just take whatever angle is given in the question and plug that in for theta with no regard for what that theta actually stands for in that formula. It's the angle between the force vector and the displacement vector. So make sure that you have a visual of where those two vectors are if you're going to think about it that way. The other way you can think about it, and a lot of textbooks don't write it this way for reasons that are beyond me, but you can also do this using the component formulation that I described in the previous videos, in which case it will be the x component of the force times the delta x, the x component of the displacement vector, plus the y component of the force times the y component of the displacement vector, which is especially useful if your force vector points just in delta X or just in delta Y direction. So for instance, the gravitational force points only in the Y direction. So the work done by the gravitational force, you'll just take the gravitational force vector, including the sign. By the way, these are force components, so include the sign in this last version, times the delta Y. Okay, so that's how you calculate the work done by a constant force vector. So let's do an example of that in the next video, and then we can talk about how it's thought about from the energy framework as well.